Percent composition. When determining the formula of a compound or discovering what that formula might be, one of the tools that a scientist has is determining what percentage by mass does each element make up of the compound. And so percent composition definition is the percentage of each element within a compound based on the total mass of that element within the compound. That's why it's called mass percent. Let's determine what the percent or the mass percent of carbon in glucose. Another way you could answer that question or reword it is to say, what percentage by mass does carbon contribute to the molar mass of the compound? So determining the molar mass of the compound is something we discussed in a previous lecture. You take how many you have of each of the elements, multiply it by their atomic mass. You'll get the total mass of that element within the compound. Add those up, and here's the molar mass of glucose. Percent composition or mass percent follows the formula. Take the total mass of the element within the compound divided by the molar mass of the compound. Because this is a percent composition, to get it to a percentage, you multiply it by 100. So because we're focusing on carbon, the total mass of carbon in this compound is 72 grams divided by the molar mass is 40%. So 40% of the molar mass of this compound comes from carbon. Empirical formulas are the smallest whole number ratio of each element within the compound. So it's a ratio that we're looking at. We're trying to find the ratio between lead, chromium, and oxygen. And we're going to be using percent compositions above to do that. You can also use a mass analysis, which starts you with a mass instead of a percent. We're going to use this poem to help us figure out the steps to follow. Here we have our percent composition of the compound, and we're going to take that and follow the poem. It says percent to mass. Because percentages are based out of 100%, there already are a ratio to each other out of 100, so we're going to take the percentages and change them immediately to masses, and that's the first step. Percent to mass. The second one says mass to mole. This is something that you learned on how to take the mass of an element and change it to a mole. Remember that a mole of any element is equal to its atomic mass. That's a conversion factor. And we do that for each of these. When you get the moles of the elements from the grams, then you need to carry at least 2 to 3 digits at this part. The next one says divide by small. Take the one that has the smallest number of moles and divide it into each. These answers are the ratios that will take the place of these x's up here. And so the final answer is written as PB1CR1O4. Here's another one that we're going to use following that same poem. We're going to take a percent to mass, mass to mole, take the percent to mass, mass to mole. Again, I carry 2 to 3 decimal places in here. Divide by small. 1.85 is the smallest. Now, is this, which could be a ratio, is this a 2 or is that a 3? Do I round up? Do I round down? This is where I need to use the last sentence, multiply by whole. If I multiply that by 2, I get a whole number. And so what I do to that one, I need to do to the other one. So my final answer is N2O5. You don't always use this last sentence, but you do in these cases, especially when they're halfway between two numbers. A mass analysis. Still going to use this poem. We were told that we have 10.87 grams of an iron pellet. So we're going to start right here on the first phrase. We already have it in mass. So here we have it, change it to moles, 2 to 3 decimal places. But now I need to find oxygen in this compound. How do I find the mass of that? The law of conservation of mass states that when you have a chemical reaction, the mass of the reactants will equal the mass of the products. So if I take the mass of the product minus one of the reactants, I should be able to find the other mass of the other reactant. And so here we have the product minus our iron pellet will tell me the mass of the oxygen. It's 4.66 grams. Again, I'm going to take mass to mole. And then I need to divide by small. This is the smallest moles. Divide them into each. This is neither a 1 nor a 2, so I will have to do the multiply to whole. Multiply this by 2, get very close to 3. Need to do that with the other one. This is my final answer, Fe2O3. But what's the difference between an empirical and a molecular formula? I like to say the molecular formula is the actual formula. Right here we're saying that the empirical formula, smallest whole number ratio, is a 1-to-1 between C and H. Well, this is also a 1-to-1 ratio between C and H, but this is the actual formula. This is benzene. So how do we determine the molecular formula or the actual one? Take the molar mass of the molecular compound, which will always be given to you, and divide it by the molar mass of the empirical formula, which you most likely have to calculate, and a ratio will be developed between these two items. Let's take a look at what was actually in your lecture notes. Here they want you to determine the molecular formula if the molecular weight of the compound is 194.2 grams. Using the formula above, we take the molecular weight of the actual compound, divide it by the molar mass of the empirical formula. Here's the empirical formula. I had to determine the molar mass of this, which is 97 grams. I get a value of 2. Now you can look at this as two ways. If I know that's the empirical formula, I'm saying that I found that the ratio is twice as much. So everything needs to be doubled up. Or you could look at that every one of those subscripts of the empirical formula need to be multiplied by 2. So this is the actual molecular formula. This is the empirical formula. Empirical formula represents that, yes, this is the ratio between them. Here's the actual formula.